Let's do some problems involving the derivative in context. The table of values below represents the values on the graph of the derivative h prime of x of the polynomial function h of x. The zeros indicated in the table are the only zeros in the graph of h prime of x. So some important things to note. This is the graph of these are values from the derivative, and these are the only zeros. All right, so on what interval is the function h of x increasing and decreasing? So h of x is increasing where h prime of x is greater than 0. So that means that h of x is increasing on the interval. Now we're not going to start with -8 because it says these are the only zeros. So that means that the values are the slopes are going to keep getting more and more positive, right? So that means our graph is going to keep on increasing, right? No matter what, the function's not going to turn around, right? The derivative's not going to turn around. These are the only zeros. So through negative infinity, we're only going to have positive values for the derivative. So h of x is going to be increasing on the interval negative infinity. And then notice here we have a 0. So negative infinity to -2. That's when the values stop being positive. And we know it's going to be increasing because h prime of x is greater than 0. It's positive. Now, h of x is only going to be decreasing where the derivative is negative. So h of x is decreasing on, right? So now right at -2, it switches and it starts decreasing. Notice that we have a 0 over here. So even though it continues to increase, it continues to decrease, we have to represent the fact that it stopped decreasing because we have a 0 there. We have a horizontal tangent at 7. So it's going to be decreasing on -2 to 7, and then 7 to infinity because it's going to keep on decreasing. And we know that to be true because h prime of x is less than 0. It's negative. Okay? So there's our first question. And so on what x value does the graph of h of x have a relative maximum? Well, to have a relative maximum, the function has to be increasing, has its horizontal tangent, and then is decreasing. Right? So if we look, let's look at our candidates first. So we have two candidates because the horizontal tangent is only going to occur where the derivative is 0. So our candidates to be a relative extrema are -2 and 7. And if we look at -2, the values to the left are positive, the values to the right are negative. So that is our relative maximum there. So h of x has a relative maximum at x equals -2 because h prime of x changes from positive to negative at x equals -2. Right? So that has to be the relative maximum. At what x value does the graph of h of x have a relative minimum? Again, we still have the exact same candidates. All right, so -2 was the relative max, so obviously it's not a relative min. So we have one candidate now, because there's 1 0 left, and that's at 7. But if we look at our graph, so let's back up just a moment. So to have a relative minimum, the graph has to be decreasing, then it has the horizontal tangent. So we're looking for the derivative to be 0, and then it has to increase. So it has to go from negative to 0 to positive. Notice, though, at x equals 7, the derivative goes from negative to more negative. So h of x does not have a relative minimum because h prime of x never changes sign from negative to positive. If h of 3 equals 2, what is the equation of the tangent line to the graph of h of x at x equals 3? What is the equation of the normal line to the graph of h of x at x equals 3? All right, well, first of all, one nice thing, so we need two things to write an equation of a line. One, we need a point. We have the point. You plug in 3, you get 2. So 3, 2 is the point. And then we need the slope. All right, so let's find the tangent line slope. Well, we don't have to look very hard. Right? All we have to do is look where x is 3, and we see the value of the derivative is negative 3. And we know that the values in the derivative are the slopes of the tangent lines for all the different values of x. So the slope of the tangent line is m equals negative 3. The normal line is perpendicular to the tangent line. And we know perpendicular lines have slopes that are negative reciprocals. So if the slope of the tangent line is negative 3, the slope of the normal line is positive 3. Excuse me, is positive 1/3. I wrote 1/3, I should say 1/3. All right, so let's find the equation of the tangent line. So y minus 2 equals negative 3 times x minus 3. My shadow kind of blocks. So that's a perfectly good equation of the tangent line. Actually, maybe I should label tangent line. We're going to have two equations here. We could also move the 2 over, so that would be y equals negative 3x minus 3 plus 2. Or if you like it in point-slope form, slope-intercept form, you can just simplify that out, and that would be y equals negative 3x. Negative 3 times negative 3 would be 9, and 9 plus 2 is 11. So any of these are perfectly good, right? So any one of those three. Made my box a little high. All right, so any. All right, now let's write the slope, write the equation of the normal line. So y minus 2 equals 1/3 x minus 3. And you can leave it like that, or you can move the 2 over, that modified kind of point-slope form. Y equals 1/3, it's like a cross between point-slope and slope-intercept. Y equals 1/3 x minus 3 plus 2. And if you want to put it into slope-intercept form, all right, that's easy enough to do. Y equals 1/3 x. 1/3 times the negative 3 would be negative 1, plus 2 would be plus 1. So any of those are perfectly fine. All right, so when we have a table of values for the derivative, we have the slope values for the function, the tangent lines at various x values. All right, so now let's look at two more questions. And actually, I'm going to skip one of the questions, and then the other question I'm going to answer. So same graph and all. We are going to save the tangent line approximation until second semester, because we will be looking at that. We'll be learning all about that in the second semester. So I'm just going to save that question. But let's answer the two limit questions. So find the value of each of the following. The limit of h of x as x approaches negative infinity. Now, I don't know exactly what the graph looks like. This is just kind of makeshift. But we do know that since the slope is positive, right, since the derivative is positive up until we get to negative 2, right, something or other, where we have this relative maximum, and then the function starts to decrease again. Right, so if we're looking though at the limit as x approaches negative infinity, we want to know where is the function heading as the x values get smaller and smaller and smaller. Well, for this graph to have a positive slope, right, if we look to the left, it must be approaching negative infinity. Right, and that's what would give it those positive slopes. Right, so and then we want to find the limit of h of x as x approaches positive infinity. All right, well, kind of the same graph there. After it gets to that relative maximum at negative 2 whatever, right, the function decreases, right, and it keeps on decreasing. Right, and actually it has some kind of horizontal tangent in there at 7. But it's not a relative max or min because it keeps on decreasing. All right, so we have to think, where is the function headed as x approaches infinity? So now we're looking to the right. So as the x values are getting larger and larger, where's the function going if the slopes are negative? Well, it's going back the other way, back to negative infinity. So both of these limits were towards negative infinity. Okay. And I'm going to pause here, and I'm going to start the next problem. All right, bye for now.